Greetings everyone, we are Group 2 and we are here now to present about our work on our project CrowdDoing Preventive Derivatives. As per our objective, we are here to develop a health score that can show the healthy and unhealthy regions of the forest using weather factors. Meet our team where we have myself, Benson Fernandez as the data analyst, Jeevitha Murugan the developer and Jashanpreet Singh the business analyst. We have the current progress of our project where we are about 74% complete on our overall tasks. We implement the standard project management practices and procedures while working on the project. Our requirement phase consists of the project charter, project proposal, initial dataset collection, and tool selection. The design phase contains data cleaning and preparation, along with some analysis and designing the formula for calculating the health of the forest. Next is the development phase, where we had implemented the formula on the collected weather data and integrate the result into QGIS. And finally, we are in our testing phase, where we are gathering all our results and interpret them visually through maps in QGIS, and we also validate if the values are correct as per our methodology. We will start with our requirement phase. As we are not given any data to work with, we took some time and effort to find the right data for a project. Some of the data selected includes land cover classification of Canada, ecological domain, tree species, and forest fire data. All these files were more than 1 GB, hence it was difficult to find the right tool to work with these huge data sets. We finally decided to use QGIS tool to work with the TIF files, and we have received confirmation of the same from a client. To work on the forest health project, we also have to classify the forest based on its type. So we have classified a total of 13 forest types for a project. After discussion with the client, we decided to work on a single province, hence the province of Alberta was selected. But we couldn't find a suitable map of Alberta alone. Hence, we used the entire map of Canada and a shape file of Alberta to extract the portion of Alberta from the map of Canada. This process involves the use of raster extraction by layer option. The entire operation took around 2 hours to extract the portion of Alberta from the Canadian map. Next, we require the research and collection of weather data. We were able to collect the weather data from over 100 weather stations on a daily basis for a range of 5 years from 2019 to 2023. We require the weather factors such as minimum temperature, maximum temperature, rainfall, humidity, and wind speed information for an area on a daily basis. Next, we move on to the design phase. We analyzed the data that we already collected and found some interesting observations. We used Jupyter Notebook to run some basic analysis on the data. We have 3 charts that were developed for the analysis using Pandas, NumPy, and Matplotlib. We have clustered line chart that depicts the total rain and maximum temperature for each year. To develop this chart, we first group by all the timely data into months using group by function, followed by a custom function that uses a plot function for max temperature and rainfall for each month in every year. Next, we have 2 bar charts that were both plotted using Matplotlib plot function, and the option bar is set for both the charts. The first chart gives the top 5 months within the 5 years that had the highest temperature. The second chart gives the 5 months with the lowest rainfall. After our data analysis, we move on to process and prepare the map for a project. After extracting the map of Alberta, we created a grid on the map so we can calculate the health scores for each grid. We select the option vector and choose the option research tools, and finally set the option as create grid. We select the grid type as rectangle. Then we set the grid extent to the map of Alberta. Then we set both the horizontal and vertical spacing for each grid. Both the horizontal and vertical spacing are set to 100,000 meters, so the grid is generated as per the distance in the map. We also need to set the CRS for the grid, and we set it as the same as the map of Alberta, so we can add it as a separate layer. Once the grid is applied, we can see that the grid is applied all over the map. Next, we enable the visible markers for our weather stations of Alberta. We modify the symbology for this layer to make all the weather stations appear as red dots across Alberta. So we can see there are some grids that have one weather station, some have more than one, and some have none. I will hand over to Jeevitha to walk you through the next steps of our project.
Thank you, Benson. Hi, Professor. I'm Jeevitha Murugan, developer in this project. So today I'm going to explain about the design phase and the development phase of this project. With the map and grid setup along with the weather stations, we can now design the weather formula needed to calculate the health of the forest based on weather factors for all the weather stations. After a long research, along with some trial and error methods, we have devised a linear interpolation formula for calculating the health of a forest. We multiply the scale and importance of each weather factors and all the values, but this is not a simple task. First, we have to assign the importance of weather factors for each forest type. We also need to make sure that sum of all these weather factors should be 1. Next, we have the scale of weather factors, which is calculated from the actual value of particular weather factors. Let's look into this one in detail with an example. For example, let's take a temperate or subpolar needle-leaf forest type. We have the healthy and unhealthy spectrum for weather factors, but we need to simplify it even more to calculate these scale values. Hence, we have the scaled it down as below. We scale it in such a way that 0 to -1 resembles the unhealthy spectrum and 0.1 to 1 is healthy spectrum for a particular weather factors. That gives us 20 values if we have a scale within 0.1 increment or decrease. But in weather, we have two extremes, too hot or too cold. Hence, we need to scale the values for both the ends of the extremes. So we have a total of 40 scale values for each weather factors as displayed. So as per the table, if the weather for a particular day contains a maximum temperature of 17 degrees Celsius, we select the scale value of 0.7 to the formula. This is done for all weather factors. Next, we need to assign the importance. After our research, we have assigned the importance as follows. So maximum temperature with the influential temperature of 32%, minimum temperature with the notable importance of 24%, and total rain with a considerable importance of 12%, and humidity with a notable importance of 24%, and wind speed with a slight importance of 8%. So if we add them all, we get total of 100%. So as per the example, if you multiply the scale with importance and add them up together, we get the total value of 92.4%. So the above methodology is implemented on the weather data for Alberta region from the year 2019 to 2023. And all the yellow columns are scale values and the green values is the final health percentage for a particular day for a certain weather stations in Alberta. As we see, there are some negative values in the health that indicates the health of the forest has been deteriorated because of this weather. So in the slide 16, we have the full data with the health percentage for all the weather stations. So we have loaded them as a layer in the QGIS and we can see its attribute table as in the slide. We check for any errors or garbage values before proceeding to the next step. As we need to calculate the average health of each grid, we need to combine the grid layer to the health data layer. So we use the option to join attribute by location with summary option enabled. Then we enter the input layer as a grid and health data layer as the data layer, and we then set the column health and the calculation or summary as mean or average. This will make sure that the averages are calculated for all the weather stations inside a particular grid only and not from outside the grid. So then we click on the run, which might take a considerate amount of time since the data set which we are using is very large and we had to do some complex conditions to calculate the average in every grid.
Thank you, Jeevitha. I am Jashanpreet Singh and the business analyst of this team. I will be presenting the next part of what we have done so far. Once the process is complete, we can see that there are percentage values assigned to the every grid which represent the average health of the forest for a particular grid. We do observe that there are some squares with no values. That means there are no weather stations to calculate the health percentage from. To find the values of the missing squares, we have the option to use interpolation using neighbor values to calculate the missing values. We have used the IDW interpolation. Inverse distance or weightlifting interpolation is a method used in geographic information systems and spatial analysis. It is a type of deterministic method for multivariate interpolation with a known scattered set of points. We set the vector layer as the grid layer and we choose the attribute as health. Then we select the distance coefficient as 2, which is normal for this map setting. We also set the extent to the grid extent and enter the distance of height and width of each box. Once we click run, it takes about 2-3 hours for the process to complete and check all the information. Then the forest health is calculated for all the missing squares. Once the interpolation is complete, we observe a heat map which still does not provide too much information. We then select the raster pixels to point from vector creation option to convert the pixel values to point values. Once it is done, we can observe a new layer that is added to the project, and if we select that layer, we can see the values for all the missing boxes as well as the graph which provides the health of the forest. Thus we were able to identify the health of a particular forest type all across Alberta from 2019 to 2023. Next are the current activities which we are working on right now. We have received an approval from the client for all the before mentioned processes of calculating and integrating health in QGIS. We are also developing the map and weather data combinations for all the remaining 12 forest types. In addition to this, the secondary objective will be completed by the final presentation, and we will be showing that in the final presentation itself. Next are the challenges which the team has faced since the beginning of the project. We were provided no data to work on, so we had to find the data on our own. As the data needed for this project was aerial and satellite images, which is not easily accessible as most of the sources which provide that data are paid. So we had to invest a significant amount of time on searching the data itself before the beginning of the project itself. So gathering and getting approval for the data based on the requirement of the client was a challenge. In addition to this, there was no forest expert or weather expert in our team. Therefore, we had to learn a lot of things from scratch, and this also took a significant amount of time and was a challenge. Next is the QGIS tool. As TIFF files are really large in size, finding a suitable software was a hassle. QGIS is a free open source software, but we are completely new to the tool. Next is the change in scope initiated by the client. The client had updated the scope twice, which had us rework most of the elements of the project we had worked until then. Next are the limited resources and infrastructure available for this project. This project requires more computing power than what is available to us, as we work on TIFF files of huge sizes, and repeating long and time-consuming process over 13 forest types is a challenge. We did follow all the entrepreneurial strategies while working on this project, which include monitoring and evaluation, data acquisition and analysis, collaborating with stakeholders, compliance and regulation, prototyping and proof of concept, technology integration, and marketing and adoption. Now the project timeline. The handover of deliverables is scheduled on 6th of December and the final presentation is scheduled on 8th of December. Now the project cost. The project has a clear budget plan to carefully control spending on key tasks. We are keeping close watch on our actual cost to make sure they match our planned budget. This is it from us. Thank you, Professor.